All right, so in the last video, we did a visualization of what this would look like if the null hypothesis were true. And again, this is not anything I'm actually going to ask you to plot on a graph. This is just, a lot of you had mentioned that you were visual learners and seeing stuff drawn out was helpful, so I'm trying to accommodate for that. So let's go back to our scenario of we're doing an evaluation of student stress and we're breaking it down by major. So again, let's imagine this is our population. This is how our numbers are spread out of all of the students that we surveyed. And now we're going to break it down by these three majors: math, education, and business. For some reason, these are the majors we're interested in comparing. So we're doing an ANOVA, right? Because we're comparing more than three. If we just wanted to compare two, we could have done a t-test. We're doing an ANOVA because we're comparing three. So remember, recap part two. In an ANOVA, you're proposing there is natural variability in every group due to chance, outside factors that we're not observing, lifestyle factors, whatever. And in the null hypothesis that we visualized before, we're saying that's really the only difference. They're pretty similar, and there's those chance variables, and that's the only difference. There's no other condition that's making a difference. For our research hypothesis, maybe we want to say, at this pretend school where we're doing this survey, their education program is known for being very rigorous, very stressful. We think that education majors are going to have a higher stress score than math majors or business majors. And so this is what we're wanting to look at. All right. So let's say in this pretend example, again, this is our population. Let's say in this pretend example that the mean for the education majors is all the way over here. And we don't have very many scoring down here on the low end. Like, let's say that their distribution is looking something like this, and that they're basically bringing this up. They're accounting for the higher average. Let's say that in this program, the business degree has a reputation for being, very, very conducive to facilitating students having low stress levels. They have a lot of extra programs, student stress relief services. They have a pretty light program. And so let's say that within this program, the business majors tend to be on the lower end of stress. Let's say our business majors are looking something like this. And then maybe our math majors are somewhere over here in the middle, right? Let's say maybe math majors are still, maybe they're lining up with the mean. So you can see how mathematically this could still work out, with where our grand mean is over here. But now we have a very different situation where if I'm measuring the mean of the education majors compared to the overall group mean, this is now a much bigger gap than what I was seeing before. If I'm measuring the mean of the education majors compared to over here of the business majors, right? I can see just by plotting this out, this is a pretty big difference. And again, I'm looking at this in ratios. So what I would be saying for a statistically significant result is this, remember, this is called the between groups variance. That the variance between these groups is going to be greater than the variance that I'm documenting within these groups. So comparing these individual education scores to the group mean of the education majors is going to be a smaller amount of variation than if I compare the average score of the education majors, the mean score of the education majors, to the overall mean of my population. And that is how you would come up with a visualization for what a statistically significant result in an ANOVA would be. So now we're going to break down what this actually means with the theory behind these testings and how to do it on PSPP. But that's your quick visualization of what it is that we're working with.